So in this video, we're going to start talking about rotation of objects about a moving axis. And all that really comes down to is things that are in motion and rotating. So suppose we had like a wheel. So this wheel is moving along a level road. What we can do and what this hinges on is that we can separate it into two different types of motion. We have translational motion, that's linear motion. And then we have rotational motion. And so we can think of them and deal with them separately, and then we just stick it all together and we're good. So if we take the translational motion of this wheel along with the rotational motion of the wheel and we add it together, well, then we get rolling without slipping. Slipping refers to down here at the bottom, so we're not spinning out the tire. It's just rolling nice and smooth along the surface. And the first thing we're going to do is we're going to take an energy perspective. So we're looking at energy. So from energy, let's first just deal with translation. So that's we're ignoring the rotation. So we're just thinking it's sliding along like that. So if it's sliding along like that, then each piece of this thing is moving with some velocity. So we'll have velocity there at the center. We can go out to the edge. And I can draw these little vectors because the whole thing is just sliding this in this direction. So I could do this anywhere, but we're going to pick the center and then we'll do 4 points along here to kind of talk about what's happening when we put it all together. And so the way to describe this is that all of these are moving with the same velocity, and it's this velocity. The easiest way to deal with it would be the velocity of center of mass, so cm. And it's the same all the way around here. So I'm not going to write them in. So from an energy perspective, this has all kinetic energy. So we'd end up with 1/2. I'm going to use big M for the whole mass of the thing times the velocity center of mass squared. That would be our kinetic energy for the translational motion. Okay, now we need to go over and think about the rotation. So we have some angular velocity like this. And the at any instant in time, so we're kind of just thinking about, just one little nanosecond, what's happening, not as it moves. So if we think of it as almost stationary but rotating, so we're ignoring all of the translational motion. That makes sense. Remember, we separated these. We're going to do them separately and then we'll put it all together. So the velocity of the center of mass in this case is 0. The center of mass is not changing, and so we're all good there. However, up here at the top, the point at the top is moving. It's moving with a velocity of the center of mass. That actually comes back here. So it's still rotating around like this. So at that instant in time, we still have the same velocity that's dealing there. Then on the bottom, if this is a constant angular acceleration, then this velocity has to be the same down here, just going in the opposite direction. And so we get a negative velocity center of mass. And this is going to lead us to something that's kind of difficult to think about. And then we can have some velocity over here. This would be pointed this direction. Same magnitude as the center of mass, but different direction, and a velocity here. So all these velocities are equal, but we're relating them back to center of mass. So I hope that makes sense. Okay, so now it's rotational motion about the axis of rotation through the center. And so we would just get the kinetic energy, so plus the kinetic energy of the rotational motion, which would be 1/2 I omega squared. Okay, so now we put it all together. So this plus this equals this, and this is our motion without slipping. So going along the top, what we're going to do is just add up these vectors. So this is the velocity of center of mass, and then we add a velocity of center of mass. So when it's rolling, the top portion actually moves twice the speed of the velocity of center of mass, or twice the velocity of the center of mass. Down on the bottom, well, I have a velocity center of mass, and then I have a negative, and so we actually get a velocity of 0 on the bottom. So as this is rolling past this point right at the bottom, the point of contact is not moving for a split second. And then we can combine these other ones. So this one and this one would create a velocity vector that's kind of like that. So it's actually at 45 degrees. And on the other side, it would point down and forward if we do that vector addition, 45 degrees to the horizontal. Okay, so this is how this is rolling without slipping. There's no velocity on the bottom part and twice the velocity on the top. And what this tells me is this is the kinetic energy, the total kinetic energy. So the sum of the kinetic energy for rolling. And when I say rolling, it doesn't necessarily have to be on a flat surface. It could be going, it could be falling, like we'll do a yo-yo example, you'll see. But the approach is the same. The axis of rotation is moving. All right, there is one other type of energy that we would have to deal with, and then we can get our entire our entire equation for energy is down a ramp. So if you have an object rolling down a ramp, you know what, let me redraw all this. Because all we need to say is that we have velocity center of mass here, and we have angular. And that indicates that it's rolling down the ramp. Okay, so our total energy here, our energy is going to be the translational kinetic energy, so KE translation, plus the kinetic energy of rotating, plus we're dropping in height, so we're going to have gravitational potential. So our total energy would be 1/2 mv center mass squared plus 1/2 I omega squared, it's omega not W, plus mg y center of mass. So be careful when you measure this. So we measure right to the center of mass. So this would be our y, or our height, or our delta y, or whatever you want to call it. Not whatever, but you get the idea. Those are all the same thing. So that would be the total energy of this ball as it's rolling. So we can use this to calculate, to do some problems and figure out like velocities and that sort of thing. The other thing, one other thing that we need to add in is the condition. So our condition for rolling without slipping. Condition for rolling without slipping. And basically what it does is it just relates the angular velocity to the velocity of the center of mass. So if you look up here, if this were a distance r, radius, then we can go from angular to the velocity of center of mass. I know it's up here, but it's also here. So this is how we're going to link it. So what we get is that the velocity of the center of mass is going to be the omega times r, or r omega. So that's how you can go from one to the other. Now, when you do these problems, we're going to end up doing both. So we got to work both in over here. Or actually, for that'll come up when we do dynamics. So let me set up some examples, and then we can work through these. So let's suppose we have a hollow cylindrical shell, mass m, radius r. It rolls without slipping on a flat surface. We'll just keep it flat. So it's a cylinder. It's rolling without slipping. What's the total kinetic energy? And then how does that compare to sliding? So compared to sliding. So first let's do just sliding. So suppose this thing were just sliding. So we just had translational motion. Then the kinetic energy would just be 1/2 of the mass times the velocity center of mass squared. So that would be the translational. So our total though, our total kinetic energy is going to be our translational plus our rotational. So what we'll get is 1/2 mv center of mass squared plus 1/2 I omega squared. And then what we probably want to do, since we want to compare it over here, is get everything in terms of the velocity of center of mass. So it's rolling without slipping, so the velocity of center of mass is r times omega. So omega is going to be v center of mass over r. So then we'll substitute this in. So we get 1/2 m v center of mass squared plus 1/2. And then we need the rotational inertia for a shell, which is mr squared. So we get mr squared times omega. And so we plug this in and square it. So we get velocity center of mass over r squared. And then let's simplify. So we get 1/2 m squared plus 1/2. That would be mr squared. But what I'm going to do is some simplification. We'll get an r squared. We're going to square this. So we'll have r squared. So the r squareds are gone. And then so we get m v center of mass squared. And 1/2 plus 1/2 is just 1. So we get m v center of mass squared. So we can see that basically it's doubled. So we get double the kinetic energy when it starts rolling. And it makes sense. It takes energy to slide it. It takes energy to roll. If we put them together, it makes sense. But it's nice. It's convenient. It actually just doubles. Now that's for this one. I'm not saying that's for all the time. We're just looking at that. Let me set up another example. Okay, here's your next example. And by the way, what I recommend you do is after I set it up, you pause the video and then try it yourself and then come back and watch the solution. But basically, this is like a yo-yo. So we have a solid disc with a string that's wrapped around it, and the string is actually, it goes all the way around. It doesn't slip. So what we're looking at basically is rolling without slipping. A yo-yo just rolls along the string. And what we want to do is find the velocity of the center of mass after it's fallen a certain distance. We'll say h. So how fast is it going? It's the velocity of center of mass down here at the bottom. We're not pulling up, so we're just holding it and letting it fall. So go ahead, you should pause it and try this. Okay, so for this, we're going to use an energy perspective. And so your total, let me erase that. Your total energy initial is equal to your energy final. That's the conservation of energy. And so we think about the energy to begin with. So if it starts at rest, then there's no kinetic. It's all gravitational potential. So we have gravitational potential. And the gravitational potential then, when it falls, if we let this be 0, so y be 0, this would be y equals h. Then all of that gravitation goes into kinetic energy. Just be careful here because this is rotational motion. So there's two types of kinetic that we need to deal with. So over on this side, the gravitational potential is going to be the mass. Oh, we'll just say mass m, I guess. So we would have mgh is equal to the translational. So 1/2 mv center of mass squared plus 1/2 the inertia times omega squared. Okay, so now we can start some algebra. So we get mgh is 1/2 mv center of mass squared plus 1/2 times the rotational inertia, So the rotational inertia for disk is 1/2 mr squared times omega. But again, like in the last one, we're going to have to change that. So remembering our constraint, velocity center of mass is r omega. So omega is velocity center of mass over r, and we substitute in. So we get v squared, v center of mass squared over r squared. I just substituted here, and I squared everything at the same time. So now we can see, well, number one, there's a mass in all of these, so we can cross that out. The r squareds are going to cancel. Now I can start squeezing stuff together. So we get GH would be 1/2 center, velocity center of mass squared plus 1/2 times 1/2 is 1/4. And then we would have just the V center of mass squared. Putting these together, this would be 2/4, so we get 3/4. So GH equals 3/4 times the velocity of center of mass squared. We flip it and multiply, so you get 4/3 GH. My computer finished its scan, that was crazy loud. GH is equal to the velocity center of mass, but it's squared, so we take the square root. There you go. There's your solution. All right. Let's do another one. Let's do a race. So this is a common situation when you study rotational inertia, and that's racing of different objects. Like suppose we had a hollow cylinder, a solid cylinder, a hollow sphere, and a solid sphere, and we release them from the same height. Which one would win? And I'll show you a demonstration of it in class, but what we want to do is just, instead of doing each one individually, generalize the whole thing. And so in general, each of these has the same, remember we're dealing with conservation of energy here, so energy final. And we're setting 0 to be at the bottom. So we're going to have gravitational potential become all kinetic. And so far, this applies for all of these objects. If something breaks, then we'll deal with it then. So the gravitational potential for all of these would be mgh, and then the kinetic. Remember, there's two types, so we get 1/2 mv center of mass squared plus 1/2 rotational inertia times omega squared. Okay. So to answer this, really, it's going to be whichever one has the greatest velocity of center of mass. That's the one that's going to make it to the bottom. Because you can imagine, okay, we have a little tiny cylinder, or a little tiny sphere and a really big sphere. So it's the center of mass that will determine the winner, not necessarily the angular. And the only thing that's different for all of these is going to be that value right there, I. But if you look up the rotational inertias, what you'll notice is that they're all of the form some number times mr squared. And that number comes out of the integration. When you actually go through the derivation for the equation, it's always going to pop out and you're left with mr squared. And so let's just say that all of them have just like c, a constant, times mr squared. So then if we can get the velocity in terms of c, then we can see what happens, and then we'll know which one would win. So mgh, let's rewrite, it's going to be 1/2 m velocity center of mass squared plus 1/2, and then we're going to use this. So c mr squared, and then we're going to change omega into center of mass, so r omega. So we get v squared, v center of mass squared over r squared. All right. So now it feels a little bit like the other one. We can cancel an m. R squareds cancel. So now I'm going to rewrite. So we get GH would be 1/2 V center of mass squared plus 1/2 C v center of mass squared. All right. So what I'm going to do is I'm going to get rid of this 1/2, so I'll multiply by 2. So we get 2gh. It's going to be v cm squared plus c v cm squared. And then we'll factor out that velocity. So if I factor out a velocity, I end up with 1 plus c times v squared. So we divide that to the other side. So you get 2gh over 1 plus c equals the velocity center of mass, but that's squared, so we take the square root. So the velocity for the center of mass of any of these is just going to be determined, you can see, by the constant that goes in front of there. And let's think about this. So we want to have the biggest number on this side, so we want to divide by the smallest number. So it would be the one with the lowest constant here, which would correspond to the lowest inertia, which means that it's the easiest to accelerate. Let me talk through that again. We want the biggest number here, so we want the smallest number here. You know, this number is not going to change, it's 2gh. And if we divide it by a very, very, very small number, it's a big number. If we divide by a really big number, this is a really small number. The square root, it doesn't matter. The overall effects are the same. So we want a very small c. So we look at the rotational inertias, find the one with the lowest constant out here. That means that I have the lowest inertia. And low inertia means it's easy to accelerate. So it's going to get up to the highest speed. So whichever one it is, I don't know what they are off the top of my head. Okay, so that's it for the energy perspective. I know this video is getting long, but you also need to be able to work with this from a dynamics perspective. So let me clear this, edit, clear. I'll try to go fast through this. So basically, if we have an object in motion, we'll go back to rolling. So we have both angular and tangential. Then we can analyze it through forces. So this is a force perspective. And there's two things we're going to have to do. So one is for the translational. And what that would say is that the net external force is equal to the mass times the acceleration of the center of mass. That's just Newton's second law. So any external forces acting on this translationally, I can't speak. Well, what I mean is that any forces acting on the object will create an acceleration on the center of mass. Okay, this is nothing new. Rotational, we learned Newton's second law for rotational, and that's that the net torque. So the net torque is going to be the rotational inertia about the center of mass creates an angular acceleration. Okay, this one is important because this is one of the requirements. So only if, number one, the axis through the center of mass is an axis of symmetry. So if your axis was down here on the bottom, that wouldn't work. That doesn't have symmetry. It's only right here, and then we have symmetry about this. It also wouldn't work if you're talking about a dumbbell with two big masses like that. You know, if you had your axis here, it's not an axis of symmetry. We don't have symmetry here. So you have to be careful with that. It depends on the type of object. And number two, the axis doesn't change direction. So this one we'll have to assume, you have to make some assumptions sometime. Like if you're riding a bike, then typically what you'll do is you rotate, you kind of shift the bike back and forth as you're pedaling. So then this doesn't hold. So like if we were going to do a bicycle, we would assume, okay, you're not moving back and forth as you pedal. You're just keeping it nice and vertical. It's not going back and forth as you move. So yeah, that's it. So we can do some problems. Let's look at that yo-yo again. So let's go back, that yo-yo. Remember we were standing there holding it and letting it fall. Okay, so now what we want to do is use a force perspective to figure this out. So translationally, that's just falling. So let's draw a little force diagram acting on it. So you're going to have tension, which is acting up like this. And then you have the force of gravity acting down. And the force of gravity acts at center of mass. That's important because when we get to torque, in this case, it's not torquing the object. And so we can start with Newton's second for the translational piece. So we'll write like translational. So translational, the net force equals the mass times the acceleration in the y direction. And my net force here is going to be force of gravity. We could call it down, that'll be positive. So it would be the force of gravity minus the tension is going to be mass times the acceleration in the y direction. Okay, so we'll have to come back probably, but now we know the acceleration in the y. But let's go over to rotation and see what we can do, because we're kind of stuck. We don't know the acceleration in the y, don't know tension. Well, I guess we could. We could get tension is going to be mg. But anyway, let's go over to rotation and see what happens. So rotation is going to be the net torque, which is the inertia about the center of mass times the angular acceleration. So the net torque is going to be the tension, and then it's acting at a distance r from the axis. So times r is going to be the inertia, and the inertia for a disk is 1/2 mr squared. Times the angular acceleration. Okay, but then we can get the angular acceleration. Remember, so this acceleration in the y, that's the whole object, but that's also the acceleration of the center of mass. And so we can get this one in terms of center of mass, because the acceleration of the center of mass is just like velocity, is going to be r times the angular. So what we end up with is that the tension times r is going to be 1/2 mr squared times acceleration center of mass over r. So we see, let's see, this r is going to cancel one of these, and this one's going to cancel the other one. So we get tension is going to be 1/2 m acceleration. Now let's take, let's take this and plug it back in here, see what happens. So we get, I'm going to go ahead and change this. So this would be mg minus 1/2 m. The acceleration of center of mass is equal to the mass times the acceleration of the center of mass. They all have mass, so we can cancel that off. And then we can get the acceleration. So if I add that over there, we would get g. That'd be plus 1/2, so we get 3/2. The acceleration of the center of mass. Flip this over, so 2/3 g is the acceleration of the center of mass. So now we know how fast it's accelerating. So what's the velocity? Well, the velocity of center of mass. Well, I have a position. I don't know anything about time, so the only one we can use is going to be that. And that would be v naught squared plus 2a times the displacement, which is h. This is 0. I'm sorry, that's 2a times h. So the velocity of center of mass squared would be 2 times 2/3 g times h. So we have velocity center of mass. It's going to be 2 times 2 is 4/3 gh, and we take the root. And I believe that's the same answer we got for the previous one, root 4/3 gh. So we did an energy perspective, and we got to the same point. Okay. One other thing I just want to show you. I know this video is like super long. So one last thing is just force diagram for I'm just going to draw the force diagram, and then you can end the homework. When we analyze forces of a ball rolling without slipping on, oh gosh. So this is rolling without slipping. So we have an angular velocity, which is turning it. And then we have a velocity center of mass, which is this way, down the ramp. And what I want to do is just draw the force diagram for what's going on here. So number one, you'd have theta down here, and then we would have force of gravity act straight down. I'm going to extend it just so that you can see it. So this would be the force of gravity. Okay, third, normal force coming up right here. You have to know how to draw these. The normal force. And then since it's rolling without slipping, it won't slide. That's the idea. So to prevent the slipping, we have to have friction acting this way. So this is the force of static friction. Okay, that's your force diagram. So you can see that if you're going to start doing what we just did with forces and torques and stuff, this frictional force creates a torque on it. And then translationally, we're going to have to deal with components. So you're going to have an Fg in the x direction here and in the y. Be careful, I'm drawing a component, but that's not a torque over here. So it's Fg in the y. Theta would be down here. You can also draw it this way. I didn't do that because the normal force is in the way. So this Fg would be acting on the translational piece. This is what's causing the acceleration, the tangent, not the translational. Let's do this. Down the ramp, so in the x. And then the force of static friction is creating the torque to torque this thing around. You also have to attribute, this also contributes to this. So it'd be like this minus that. All right, so we'll do some of these in class, and that'll be it for now. It's way too long. Sorry.